Okay, we're going to pick up where we left off in our last video about logarithms and how to linearize exponential graphs. This time we're going to look at graphs of the form y equals ax to the power of b. So this time it's not exponential. It may look very similar. Notice that we now have a y-intercept of 0 and it's the power of x that we're unsure of. Before we suspected that our function was some constant to the power of x. So this is the graph that we're trying to find. Remember, you may be given this as a series of points, so we can't differentiate because we don't know what that power is. Okay, so let's start off same as we did before. We're going to take logarithms of both sides. And same again. We're then going to split this into a multiplication, split this multiplication into an addition. Sorry if you've got some background noise. Bring the power to the front. Okay, so you can see it looks very, very similar to what we got when we had something which is in exponential form. However, now we notice that it still looks kind of linear. We still have something of the form log y is equal to some constant times an x variable plus another constant. However, what we need to notice in this case is that we now have a log x axis as well as a log y axis. It will still linearize it, because if we plot log x against log y, this can still be equivalent to m. That will take the place of where we usually see our x, and a plus c. So we should still have some sort of graph which looks perhaps a little like this. Our y-intercept, again, our plus c, is log a equals your plus c. Nothing changes there. However, our gradient, so if we calculated the gradient of this graph, m in this case would literally be our b value. So there's no need to do 10 to the power of your gradient in this case. That's why it's very important, because the two forms look so similar but have different results. Go through this process each time until you're very, very comfortable with what it should look like. Take logs of both sides, rearrange it, and then identify what is in the place of your x, what is in the place of your m, your gradient, and what is in the place of your plus c. Okay, so just like before, let's see how we work through that and see what it actually looks like. So if we just take an example, let's say that we have our graph, and let's give ourselves a negative gradient this time. Why not? It will still work exactly the same. So we have our log x-axis and we have our log y-axis. We'll say that we know the x-intercept. Let's say that is 3.2, and we'll say that we know our gradient. So remember, if you were given points, or you were given this as a graph and you needed to find the gradient, go for the biggest triangle you can to minimize any error. And let's say we have a gradient here of minus 0.28. Okay, so we will look at our original form and our logarithmic form, and we notice that b is just the value of our gradient. Okay, so looking at that, b is our gradient, 0.28, and similarly log a is our y-intercept. So again, in order to find a, I'm going to need to do 10 to the power of 3.2. Putting that in my calculator, That gives me 1,584. Remember, when we're using log base 10, this is basically telling you the size of your number. That's going to be in the thousands, a 1 with 3 zeros behind it. The 0.2 is just the rest of that number in there. Okay, but that first digit tells us the order of magnitude. It's going to be in the thousands. Okay, so now we have our A and our B. We can write down the original form, y equals 1,584x to the power of b. We have our equation. We can then use that to model new values of x, new predictions of y values given an x value.